Hey guys, welcome to the machine learning tutorial series, and in this episode we're going to look at normal distribution. Assume that there are thousands of people in a particular locality and you take a survey of monthly income of all those people and you plot a histogram with that data where x-axis is the income bracket, say 0 to $500, 500 to $1000, 1000 to $1500, and so on, and y-axis has the count of people in each income bracket. Assume that the average income is about $4,000. You can find from the histogram that a large number of people are earning between $3,500 and $4,500, that is close to the mean of $4,000. Fewer number of people earn between $3,000 and $3,500, and also between $4,500 and $5,000. And even lesser number of people earn between $2,500 and $3,000. A few proportion of the people earn extremely high, like above $6,500, or extremely low, like less than $1,500. So the majority of the people earn around the average income. A small proportion of people earn extremely high, and a small proportion of the people earn extremely low. This is the case with almost any real-time data which is sufficiently large. For example, even if you take marks of students, there will be a large number of students getting around the average marks. Few students get extremely high marks and few students fail. Not only marks and income, but most of the real-time data's histogram will have a bell-like shape similar to this. Now this histogram looks like this smooth curve, and you can see that it looks like a bell-like structure. This bell-like structure is called a normal distribution. Now I have this normal distribution of the monthly income of people. X-axis here is still the income, but in thousands. So 4 here is $4,000 and 5 here is $5,000. Some interesting features about this normal distribution is that the mean or average is at the center, here represented by the green line. And the normal distribution is symmetric about the mean. So the portion to the left of the mean, represented by the red region, is symmetric to the portion to the right of the mean, represented by the blue region. There are two parameters which decide the size and shape of this normal distribution. Let's look at them. Now, if everyone starts earning $1,000 more than what they had already been earning, then the average income also increases by $1,000 from $4,000 to $5,000. And so the mean of the normal distribution also shifts to the right to $5,000. And if everyone starts earning $1,000 less than what they had already been earning, then the normal distribution shifts left so that the mean is $3,000. So mean is one of the main parameters of normal distribution which decides its position. Now the highlighted portion in red represents the poorest people who earn less than $3,200. And the highlighted portion in blue represents the richest people who earn greater than $4,800 per month. Now, if the rich get richer and the poor get poorer, then the normal distribution becomes relatively flatter, and you can see that the red and blue portion becomes bigger. So now there will be more people who are earning extremely high or extremely low than the previous case. What has changed before and now is the variance of the data. If the variance is big, then it means that there are a large number of people whose earnings are farther away from the mean, which is in the current case. And if the variance is small, then it means that most of the people's earnings are closer to the mean and very few people's earnings are farther away from the mean. Currently, you can see that there are no people whose earnings are less than $3,200 or more than $4,800. So there are two parameters which decide normal distribution. First is the mean, which decide the position of the normal distribution, and second is the variance, which decide the shape of the normal distribution. The square root of variance is the standard deviation. So the function which defines this bell-like structure is called probability density function of normal distribution, which is shown here on the left. It takes two parameters, mean and variance. So m here is the mean and s is the standard deviation, which is nothing but the square root of the variance. So if you know m and s, then you can easily generate this curve for different values of income. Just a note here is that both mean and standard deviation are in thousands. We are currently dealing with monthly income of people from a particular locality. Now, if I walk up to some random person in that locality and ask what his monthly income is, I want to know the probability that he says a number less than the mean of $4,000. So I want to find the probability that I find a person from the red region, which can be done by calculating the area of the red region. That is the region to the left of $4,000. For the same, you can integrate the probability density function, which has a mean of 4000 and standard deviation of 0.4000, from minus infinity to 4. And from the result, you can see that the probability that a person having an income less than $4,000 is 50%. Here, 0.5 represents 50%. In fact, you can integrate from minus infinity to infinity and find that it is 1, which represents 100%, which is the total area under this whole curve. Pretty obvious because people can earn only within this range. Another example, now I want to find the probability that that person earns less than $3,200, and for the same I integrate from minus infinity to 3.2 and can find that the probability is 2.2%. Now, since normal distribution is symmetrical, the area of the red region is same as that of the area of the blue region. That is, the probability that a person earns less than $3,200 is same as that of that person earning greater than $4,800. And the same can be verified by finding the area of the blue region by integrating from 4.8 to infinity. And we get the same probability as that of the red region. Now, one important note here is that normal distribution is a continuous distribution, and hence you cannot ask the question like, what is the probability that a person earns exactly $4,000? Because in a continuous distribution, the probability that a particular number occurs is always 0. It's pretty obvious, right? Because the probability is given by the area under the curve of the probability density function, and a single point doesn't cover any area under it. The same can be verified by integrating. Say you want to find the probability that a person earns exactly $4,000. For the same, you integrate the probability density function from 4 to 4 and it returns 0. Some additional points. If I want to find the probability of that person earning between $3.5 and $4,500, then I can simply integrate the probability density function from 3.5 to 4.5. Or alternatively, we can find the area under the curve to the left of 3.5, highlighted in the green. And since normal distribution is symmetric above the mean, the area of the green region is same as that of the unhighlighted region on the right. So area of the red region is simply the total area, which is 1, minus the green region and the unhighlighted region, which is nothing but twice of the green region. Alright, a small note over here, the bell curve you're seeing is, as you already know, is the probability density function. And to get the probabilities, you find the area under this curve. We have already seen that the total area under this curve is 1, which in this case represents 100% of the people. Now the second curve represents the probabilities. For example, to get the probability of people earning less than $4,000, we simply integrate the probability density function, which is the first plot over here, from minus infinity to $4,000. We know that the corresponding probability is 50%, which is represented in the second plot. In short, the second plot gives the area under the curve of the first plot from minus infinity to every point of x-axis. That's why we can see that the y-axis of the second plot varies from 0 to 1, where 0 is 0% and 1 is 100%. This is called cumulative distribution function, or simply distribution function. We can get this function by integrating the probability density function. Okay, now this is the same normal distribution we have seen, where the mean is represented by mu and standard deviation is represented by sigma. In a normal distribution, 68.2% of the data lie within one standard deviation from the mean. That is, if mean is $4,000 and standard deviation is 1,000, then as per this diagram, 68.2% of the people earn between $3,000 and $5,000, and so on. Awesome, we are done with normal distribution. Now let's see how we can work with normal distribution using R. For those who don't know R, you can skip the following part as I'm going to talk about the function R language has for normal distribution and not much of conceptual topics. Let's create a normal distribution with a mean $4,000 and standard deviation of 1000. Now the probability density function of normal distribution is given here. In this function, the only two parameters are mean, which is m over here, and standard deviation, which is s over here. We can plot this function using the simple plot command. Xlim parameter is used to set the range of x-axis for the plot. Now, if you want to find the probability of finding a person who earns less than $4,000, then you can integrate using the integrate function from minus infinity to $4,000. From the output, we can see that it is 50% probable. So we have defined a function called normFun, which is the probability density function of normal distribution. But R has an inbuilt function called dnorm, which does the same as that of the normFun function you define. So you get the manual of dnorm function using the question mark operator. On executing it, you can find that it takes 4 parameters. We will make use of the first, second, and third parameter, which are x values, mean, and standard deviation respectively. Now we can check if both does the same operation. We will find the value of probability density function at x equal to 4000 for our income data using the normFun function that we created. And we see that we got some value. Now we'll find the same using dnorm function, and we can see that we are getting the same result. Previously, we saw how we can get the probability of a person earning less than a particular amount by integrating the probability density function. The alternative to this integration process is using the pnorm function. So the below line of code does the same operation as that of the integration process we saw previously. And from the result, we can see that the probability of a person earning less than $4,000 is 50%. Pnorm function is the cumulative distribution function. Qnorm function, on the other hand, does the exact opposite of pnorm. So it takes as input the probability P and it outputs the value of income below which you can find P percentage of people. So in the next example, the Qnorm function gives the values of income below which you can find 50% of people. Okay, just a note here that I should have used the word probability instead of percentage. So on executing the Qnorm function, we can see that the output is just the opposite of Pnorm. Let me plot the probability density function again. Now we have one more interesting function called rnorm, which samples data from a normal distribution and is mostly used for simulation purpose. For example, assume that you walk up to 10 random people in that locality and ask for their income. Now you want to get an idea of the numbers they might say. You don't know unless you ask them, but you can simulate such event using the rnorm function. This line of code does exactly the same. That is, it samples 10 numbers from a normal distribution whose mean is $4,000 and standard deviation is 1000. And the distribution of the sampled values closely follow the probability density function. That is, out of the 10 sampled values, there are more values around the mean of the normal distribution than away from the mean. Now let me sample 1 million values from this normal distribution and plot a histogram of the same. From the plot, you can observe that it looks normally distributed. Now let me sample just 1000 values from this normal distribution and plot a histogram of the same. From the plot, you can observe that it looks fairly normal, but not as good as when we sampled 1 million values. If you sample just 100 values, it looks even less normal. But if you sample just 10 values, it hardly has that bell shape of a normal distribution. So why is this? You know that in a fair coin, the probability of getting a heads is 50%. So if you toss a coin twice, will you get exactly one heads and one tails? No, you wouldn't. But if you toss a coin like 1 million times, then you will get about 500,000 heads and 500,000 tails. So if you repeat an experiment small number of times, it might not exactly follow the underlying probability structure. But if you repeat it large number of times, it definitely will. Same is the case with normal distribution as well. If you sample large number of values, it follows almost the exact normal distribution. But if you sample just few values, it might not even look normal. Alright guys, we are done with normal distribution. Hope you enjoyed it and thanks for watching.